So I feel like I'm about to take everyone on like a huge left turn here.
Right.
But putting my own anxieties aside, I know a few people in the room already, but I'm hoping that like there's a lot of future friends and collaborators here in the room. So the title of my talk today is Pollution Policy Simulations in the Context of Skewed Pollution Generation Distributions. And when I sent it to Chelsea last night, I looked at it thinking like that's the most terrible title ever. But I'll tell you just a little bit of background before I get going. So, thank you so much for having me. It's exciting to be affiliated with such a renowned group here. And just as a note of background, my background is in quantitative social science, mostly in geography, sociology, a little bit of environmental science. And I'm new, to the institution in a lot of ways, but specifically, I'm interested in pollution generation and who's dealing with it. And the endpoint we're really concerned about is people's health and well-being in terms of exposure. The reason that I mentioned skewed distributions in the title is that many researchers in the field that I'm most closely affiliated with are looking at, where does pollution come from a source by source or chemical by chemical basis. And one of the weird things that we find extremely consistently is that when you put polluters into a group and you look at where pollution comes from, it's almost always an extremely skewed distribution. And as groups become more and more homogeneous, it actually becomes more and more skewed. Oh, sorry. So what this means is that the problems that we see in communities are most likely driven by a really small number of actors. And there's a lot kind of more to do about this that I'll describe to you. But before I get too in the weeds, I'll get going with kind of like how this project started. So I haven't had a chance to talk about this paper yet, and I wanted to just tell you a little bit about where it came from and a little bit about how I framed it. So I think that, like many of you, in the beginning of 2020, I hadn't really heard that much about the novel coronavirus. I'd heard some inklings of it, but I wasn't prepared for sort of what was going to happen to the world at that time. And what we saw right after 2020 were, at the beginning of 2020, were popular press like this, COVID-19 lockdowns have strange effects and air pollution seems to have gone away. And the indication that a lot of these papers or popular sources talk about is, we have this situation where we can suddenly see mountains in China that we haven't seen before. We suddenly have different changes in air pollution across urban areas, even like New York, the New York tri-state area. And one of the things that kind of made me think was like, people are touting this, and it's not that it's not great that we're seeing these changes, but do we really need to halt economies and change lifestyles to be able to do this? And because of the pollution research that I've done for a bunch of years, my initial feeling was, I don't really think so. If we know, you can find these types of papers out there. This is just from this is Forbes 2022. They're talking. People in the popular press notice this too. That 5 major polluters are driving extreme climate changes, and they can link these things to impact. So when you see this sort of narrative and rhetorical practice in society where we talk about how great it is that the change in human civilization resulted in these huge changes in environmental quality, it lacks this complexity of the socio-environmental system in which we live, right? And it doesn't embody kind of what the people who study pollution, like me, know that pollution is driven by these extreme actors. So what if instead of thinking about the world as like needing to vastly change how we live, which not that I don't think we need to do that too, but being a little bit more critical, about how we move forward here. So academics know this too. This is from March of 2023. This is a Guardian paper And it talks about how there are 1,000 super emitting methane leaks that trigger climate change tripping points. I've given you these two charismatic examples, but honestly, I could probably do this Google search, or you could, right now, and you'd find more papers that talk about this. But what I would say is that there is this body of academic literature that I'll talk about just in a second, but there really isn't sort of an embodiment of these types of patterns in how policy decisions are made. And so I'm interested in doing policy simulations or other computational approaches that leverage sort of the large scale pollution data that we have access to in our country to be able to try and think about, what kind of advice and sort of co-creation could we do with policymakers to support the decisions that they make, and to use science to make these types of decisions most effective. So in the academic literature, this is a 2019 book called Super Polluters. This is a EWG Environmental Working Group paper talking again about this non-normalcy associated with pollution generation. And I think it's uncontroversial to summarize this pattern as a key feature of society's impact on the environment, rather than a anomaly or something that we shouldn't expect. It's not something that's easily thought about. Like, we love to think about sort of averages and means and good things that describe distributions that are normal, but pollution generation just doesn't behave that way. So this type of relationship is formalized across a bunch of different disciplines, but researchers have found that some societies pollute more than others, some groups within society pollute more than others, some industrial firms contribute a lot more harm than others. And while it's not controversial at all, right, to say these things, they just don't really make it into the way that we manage the environment. And so with my interest in environmental science comes from trying to work at this intersection of computational social science and decision makers by regulators in our country. So what does this research really look like? A lot of it is coming from environmental sociologists, and they are talking about patterns that are disproportionate. And often you have this body of literature is somewhat disparate. Like, you have kind of a core group of sociologists that can probably like all have dinner at the same table together because there are not so many of us. But honestly, once I start talking to interdisciplinary groups, often this type of pattern is easy to think about, and something that is seen certainly in nature, like these sort of log normal or extremely left skewed distributions. So in research projects, what do these things look like? So often in this in this body of work, we're using metrics of inequality like Gini coefficients. So I think that the details aren't super important for this moment, but usually there's some situation where we're going to plot the cumulative share that any one actor is going to contribute based on its proportion of all of a sector or a group or a type or something like that. And so you could imagine that if you have a really equal society or a really equal pollution generation distribution, you would expect it to be across this sort of diagonal line where one unit or one sort of proportional cumulative share of pollution is generated by one actor or 1% of actors or something like that. So Gini coefficients are really commonly used in econ, in sociology, and they often are doing things they're often used to measure valued resources like income inequality, stuff like that. The Gini coefficient ranges from 0 to 1, where 1 is completely disproportionately distributed and 0 is perfectly equal, which would be this horizontal line. So in the pollution case, we find extremely high Gini coefficients. For example, this is a paper from 2016 that I should have had the citation under, but I can point you to it later. So if you look at the black line, this is all manufacturing industries from, I think 2011 is the data source here. So you can see that the vast majority of pollution generators are almost, 0% of the total. And I think if I remember correctly, there were about 11,000 facilities in this project, and about like 1,400 of them are generating 90% of the problem in this black line. So as sort of a person who's interested in socio-environmental systems and, everything from, sort of these quantitative approaches that I do, but I'm also interested in like why do these patterns persist? Why are they so easy to find? And what are the socially structured factors in society that support and help perpetuate these types of things? So one of the things I get asked all the time are things like, well, are all of these facilities, in, non-ferrous metals or something like that? Are they all located in places where, environmental regulatory decision-making is weak? Are they all located in places like environmental justice communities, which we often think about as, people who are more likely to deal with contamination in their communities because of a variety of other inequality patterns? Or, there are other hypotheses too, like do all of these facilities, maybe they're incredibly big, like maybe they are really good job creators. There's a lot of rhetoric that talks about how environmental regulatory action is going to directly impact job growth. And, that we quickly get to a point where environmentalists are, or environmental issue groups are faced with criticism like, well, if you want me to install this scrubber on your stack, then like you're going to lose the community's jobs. And so we often try and talk about these things as a what if some of these facilities are actually providing something good to the environment or good to the world, good to society, to try and like recognize the interconnectedness of these actions. So employment is one of those things that we think about. And when you control for employment, and instead of looking at, pounds of pollution or some sort of risk-weighted metric about pollution, and you do sort of like, per job pollution number or something like that, it does move this line, towards the center a little bit, but certainly not to explain for the entire thing, right? And so while there is, this growing body of scholarship, people have looked at this within industrial sectors, within specific industries, within, charismatic industries like electric power. People have looked at it between sectors, between countries. These patterns are extremely persistent, but I think that typically there's not a lot about, why does this still exist or why is this so stable? So I have spent, I guess, the better part of a decade working on this why question. And I have this on my whiteboard, and it's not something that I'm going to talk everything about today, but every time someone in a talk like this or somewhere else mentions, well, what about this or what about that? I add it to my list of like, well, maybe this is why it is existing. And a lot of these things, I don't know what the data source would be for this in it, but I do know that often we have sort of these four different things four different, sort of typologies, one might call them, to describe as to like why this pattern exists. Maybe, they're all in specific parts of the world. Maybe they have some social context like facility employment. And I highlight that because I'm going to, show this policy simulation that relates to that. Maybe it's because of some sort of exogenous facility characteristic, like how it's owned. And we certainly know some of this matters. And then maybe it's because of, endogenous or some sort of exogenous facility characteristic, like, it evades inspection, or it's, I don't know, permitting of hazardous waste generation is a political process, and it's different from everywhere. Everywhere you go, it's different, even in the United States. It's not like getting a driver's license, even though that's actually pretty different from state to state in my experience too. The purpose of this paper is to, challenge a simple view of a jobs environment trade-off. So it's it's pretty common in popular media as well as in, even some academic circles that there's a proportional relationship between environmental pollution and economic activity. And what we decided to do was to, use some of the research we had looked at in the past. We had done a lot of work in the manufacturing sector. We knew that the manufacturing sector was very non-normally distributed, where about 20% of facilities generate the worst 90% of pollution per risk metrics. And we also know that there are situations that the people who live around these facilities matter. Like, not every community gets an extreme polluter, only some do. And those communities are often what we would call environmental justice communities. And that's also some other work that we did leading up to this. So what we decided to do, and all this work ends with a, mine included, ends with a conclusion paragraph that says regulators should target, regulators should recognize this. Regulators should, maybe you get, more bang for the buck, or triple bottom line, or, double win, or whatever the jargon is, today in that arena. And I mean, us included. So what we decided to do was to do some thought experiments and simulations in the context of, none of them are super realistic, but they're meant to be crude enough that you can get an idea of what might happen if you meaningfully embody these patterns in decision making. It's a real pleasure to talk about this today. This is I did this paper as sort of a fun nighttime activity during 2020 when my 3-year-old was asleep. And so I read this paper and I have a lot of fond memories and a lot of hard memories associated with doing it, but it's a real pleasure to have the opportunity to share it with you today. So what are these thought experiments, and what do we want to do? We wanted to simulate management scenarios, like the effect of hazard reduction and employment and sort of potential job loss compared to sort of a business as usual scenario. So the business as usual scenario is like do nothing, basically. And we have 3 management simulations. We have industry level shutdowns, facility level shutdowns, and industry benchmarked facility performance standards. So first of all, quickly, you should all kind of say, there's no political feasibility in doing shutdowns, right? We're not arguing for that. We're not saying we would ever do that. We just are trying to do a thought experiment in terms of what if we did that. I think there's no regulator, there's no community, there's no one out there that would argue that you should do that. But it is an interesting way to think about it. Our more realistic, yet probably still kind of unrealistic, are industry benchmarked facility performance standards. And this is where you look within the sort of industrial group that facilities are acting within their economic sectors, and you just make them be less worse. I wouldn't even call them being good. They're just as bad as the worst actor excluding them, right? So we're not asking for huge changes in the industry benchmark. And, we haven't engaged with the sort of the hardships of policy crafting or implementation or anything like that. This is really just a midnight experiment for fun. So what data did we use? We used 2 relatively large and established data sets. So our first data set is the toxic release inventory and the risk screening environmental indicators. These come out of the comprehensive right to know legislation of the 80s after the Union Carbide meltdown in Bhopal. There was room on the political agenda for the Comprehensive Liability Act, which requires that if you hold a hazardous waste permit once a year, you have to tell the public what you released and how much of it. And all of these data are publicly available. They go back to 1988, although our project we decided to cut off the first 10 years for a variety of reasons, because these data are, regulatorily mandated. They're self-reported. So, spiral out of control related to the data problems in your own heads, right? But it is a very, very wide data set across the entire United States, every sector. There are about 50,000 facilities over the relatively long period, and it tells you kind of basic information about where the facility is, what it released, how much it released, and one of the things that we have employed is the risk-weighted version, which basically gives you a way to compare two different chemicals, right? So you might have a chemical that has a totally different fate and transport in the environment than another one. And so we need a risk weight to be able to compare the two instead of just pounds or something like that, because a pound of chromium might be a crazy amount of chromium, I guess, but it's a lot different in terms of its health endpoint than a pound of something else. There's nothing about really organizational structure or anything like that in the TRI data. So what we did is we linked with the National Establishment Time Series data via a crosswalk. These data cover about 50 million establishments across the United States, and they're really about sort of business decision making. It's not meant for this. Almost everything that I do is sort of this data synthesis approach of linking things together that aren't supposed to link together, which I think I probably share that interest with a lot of people in this room, despite the fact that our topics are widely different. This is a highly proprietary data set. We bought just facilities that have that I have the ability to crosswalk that are registered with the TRI programs. And we continue to work with the owner of these data to try and help him fix bugs and errors that we find across. So we've really become kind of partners with Donald Walls. It's been a really great partnership. Both of these data sets, the unit of analysis is facility. So what I end up with is the sort of hazard footprint of a facility and the number of employees that each facility has for the purposes of this project. So I merged these two on a provided crosswalk that, I say provided, but really it was sort of co-created because it was a challenge in itself to get that crosswalk to work. But in the end, after a lot of hand matching, I would say, we had a 92% merge rate, which was as high as we could possibly get. There's about 26,000 facilities included in my analysis. They cross every single state, every single county in the entire United States. There are 393 industrial sectors represented. And we ended up cutting off the time frame from 1998 to 2012 instead of going all the way back to 88 for a variety of decision-making reasons. The rules change over time. So, there was a big change in rules in 1998. Okay, so for this analysis, I have a facility by facility analysis of all the 25,000 facilities by industry. And I know the total number of employees that are also at every single firm. And I'm interested in the change in emissions and potentially the decrease in employees in the event of these different simulations in comparison to business as usual. So I'm about to show you a bunch of graphs, and they're sort of small, and I'm going to just orient you to sort of what I'm doing here before I present them all. So each of these, the y-axis is ranging from 0 to 1, 1 being exactly the same as business as usual, and 0.5 being a half as many employees or half as many pollution metrics, however you want to call that. So in each of these simulations, we have simulated complete shutdowns of industries, complete shutdowns of facilities, and this policy simulation where the worst facilities are compelled to be slightly better. Okay, so what do we see here? I realize these are incredibly small, and I didn't foresee this when I made the slides. They looked great on my computer, so okay, so the first thing we did was we did a random industry-based shutdown. So we shut down 25% of industries, and there's error bars around that because we did that 1,000 times just to make sure that we didn't have a random sample that was sort of special in some way. And what you see is basically we lose 25% of employment and 25% of hazard. Not too exciting. So if you bounce around off the median, you actually get none of the hazard because all the hazard lives far, far away from the median, right? But you still get about 25% of the employees, right? So about 10, if you shut down, I'm shutting down whole industry here, right? Something we would never do. And Then we moved to, sort of targeted shutdowns. So if I shut down the worst 25% of industries, we lose almost all the hazard, right? The hazard decreases, to almost nothing because the worst 25% are like all the hazard, essentially. And then I have two other targeted scenarios, one where we shut down about 10% of the industries based on, worst hazard to better hazard, and then 1%. And, what we see here are a few things. One, it's really, really stable over time. So there's a little bit of a weirdness going on here, but that's might be a reporting problem. I'm not totally sure, but I can talk about that a little more if you're interested. But what we find is that indeed, these targeting scenarios are really helpful in grabbing pollution, but they're, less bad for employment, especially if you're not the employee, right? But if you are the employee, it still really matters, right? Because you don't really want anyone to lose their job in this scenario. Okay, so the next thing I did the exact same thing, but instead of shutting down within or shutting down whole industries, instead I'm just shutting down facilities. And we see really similar patterns, although the lines are a little more stable in a variety of ways. But again, the random shutdown gets you what you thought you might get. The median shutdown gets you the opposite of what you might want. And then we have, if you shut down a lot of facilities, you get, almost all the hazard gone, but not very many. But you also impact a lot of employees. So I have some summary numbers here. So if you shut down 25% of facilities, you have a 35% decrease in employment. This is definitely not tenable. If you shut down 10% of facilities, it's about 1,300 facilities that you're shutting down across the entire United States of 25,000. And if you shut down 1% of facilities based on total hazard, it's about 133 facilities that you're working at. So there's an aspect of this pattern that is optimistic, and there's not much in climate change, environmental science, industrial pollution that's optimistic for me to talk to my students about these days. And I really like this because it takes 25,000 actors and it makes it, 133, right? Okay, so what about if we avoid shutdown because the reviewers really hated the shutdown scenario? So we needed to add some scenarios that were like less rough for the world. So in this case, you'll see that the employment lines stay completely flat because we haven't shut anyone down, right? And we haven't engaged at all with what it would be like for management to do these types of decreases. We're just assuming that they could do these decreases and not actually have to change their employee loads at each facility. We did 3 targeted shutdowns, and what we did was, again, kind of what I said earlier, we looked at the industry in which each facility is located. So if they're in the non-ferrous metal sectors, they have to be just as bad as the worst facility, not including the group, the 25% group or the 10% group. So they just go down to the max of like all of the facilities that are doing the same thing they're doing, and excluding this sort of extreme group. So in this case, if you decrease, you take about 25% down to the max of the industry in which they're located, what we see is a 82% decline in pollution footprints. And in our case, no one gets fired. If you just target 10% of actors, we end up with impacting about 1,500 facilities. And if you just target 1%, we end up only impacting about 400 facilities. Okay, so the whole purpose of this, right, is to try and communicate with policymakers about the realities of pollution generation distributions, and try and just talk to them like these are the types of scenarios in which you might consider as realistic or unrealistic as you might think. So again, this is a terrible situation for this exact room, but we tried to come up with like a trade-off frontier called sometimes. I'll help you here with this in a second. So since we had a lot of stability across time, what I did was I averaged some of these numbers for employment and hazard reduction over time. And then I'm plotting them based on the proportion of, hazard, production, change in hazard production, and the proportion of employment. And so what we see is like there's a bunch of scenarios out here, and I've named these in ways you can't read them, but trust me, I guess. These ones are like, if you do the median or these random ones, like they have a pretty big impact on employment, and they do like nothing for hazard reduction. So we identify two scenarios that are going to sort of maximize hazard reduction and minimize employment loss, and those are the performance targeted 25% and the facility targeted shutdown 10%, which obviously this one is the facility targeted 10%, and this is the shutdown, which we wouldn't obviously argue for, but I think we can still learn from it. And then the other one is the performance targeted 25%, where you really try and impact the behavior of the 25%, the worst facilities that generate the worst 25% of emissions. Okay, so what do we say? Well, we said that there were two simulations that stood out, and we also felt like it was worth it to show the ones that were terrible, right? Because it was even surprising to me how terrible the median one was. Jumping off the median gets you no hazard at all, basically. And I think that it's just like maybe the clearest, it's like one of the clearer sort of pictures of pollution non-normalcy that I've seen in a while. We also, we have people who say, maybe random selection or something like that would work. And honestly, when you talk to EPA regulators, which we do all the time, the EPA knows about these patterns, but it's a big institution. It has a lot of inertia. They kind of know who they're going to target for inspection or other types of enforcement action. And so, they are interested. They're having, while they understand these patterns, I think showing some of these simulations was helpful in realizing how extreme these pollution generation distributions are. This, I really appreciate you listening to, my interest here today. And, I have sort of two things to say in conclusion. First of all of this work I would sort of categorize broadly as computational social science. I do a lot of work in, thinking about, who are around these facilities. We do a lot of spatial statistics using R. I echo Chris in the sense that R and the SF package has made our life incredibly easy. Tidy census, tidyverse is the way to go for us. And it's a way to, all of my colleagues use this. It's almost like a boundary object where we can, collaborate over wildly different things, but using, numbers are numbers in some ways. So I think that there's a lot of translation that could happen here between scientific discovery and policy decision-making. My experience is that people at EPA are, they know about this paper, they are excited about it. It's hard to figure out how to use it sometimes, but I think they know, and they're very open. We've had a very, free flow of ideas and data use across my research group and the agency over the years. And so the conception that EPA is kind of, sitting somewhere not doing or not recognizing the computational potential of the data that they already have, I don't think is quite true. I think there are other barriers. The Trump administration really changed a lot of the way that EPA was organized. And, I think that making direct policy links, there's a lot of people that want to hear this story, but I think it's really, really important that we are connected to those groups in a very meaningful way and doing high quality, science to try and help them. And, again, they help us too. We do a lot of co-creation. And that's kind of a jargony way to say we just kind of work together to come up with research questions so that when I do it, when we came up with 1, 10, and 25 for policy shutdown and stuff and change, I asked them like, are these realistic numbers? Cause like I pick any number, it doesn't matter to me. And so I found this to be incredibly helpful and informative as you move forward and try to get people in the policy community to listen or hear or read what you do. Lastly, this is a sort of data wrangling project, right? Like there's no regression, there's no fancy math, really. There's just, like I can picture sitting in my kitchen, like working on this project. So these data sets are created, they're ready to go. And I have thought for a long time that I would find a lot of colleagues who, I didn't even know would want to use these data, but have covariates that are spatially explicit and could include in, more probabilistic or causal modeling choices. So I hope I haven't gone over time or under time or anything, but I just, I really appreciate the chance to meet everybody and to share a little bit about what my evening activities were for a while. And, this work was published in was recently published in the Journal of Environmental Science and Policy. So you can see like the whole thing there if you really are interested. Otherwise, I'm happy to answer any questions you might have.
Let me jump in. This idea of, one thread in this very broad talk is that there's this real cost to environmental impact that isn't factored into the cost of business, and I guess that's sort of like a key element in that recent report that got a lot of press, Das Gupta review.
Yeah.
And so, what is the thread that connects what you're doing into that economic story?
Well, we're not doing sort of microecon modeling the way that like a environmental economist might. We're not doing sort of optimization really. We're interested in, it's not that we never do that, but we're interested in, operationalizing an integrated system. And so right now, polluters are not required really to deal with externalities associated with their production processes. And so, we try and think about, like I said earlier, that like we're really interested in the sort of science question for me is like, well, what are the socially structured factors that perpetuate this very stable pattern? So one of the ways that we've worked with economists in the past is, so, if you live in a really unequal world where you produce, something bad at a facility that even if it has societal benefit, and if your world is really unequal, then you have the ability to transfer the externalities from your production process to a lower power group in society. And so what we try and do is think about how do you operationalize these relationships in mathematical models so that we can, speak the right language of economists or of, policy people. And, we posit basically that like, if you were to make, a society more equal, whatever that really means, you would interrupt this ability to do the transfer. And so actually a society that is more equal is a society that is cleaner, because you can't actually make the transfer you have to deal with it yourself, right? And so how that actually makes it into sort of the economic scheme of, decision-making and talk, it's more coming from like macro econ thinkers, like, Sen and stuff, who are thinking about things at a different level. But we love microecon too. We just, yeah. Yeah, Chris.
Sure, sure. So we did a project with the TRI Toxic Release Inventory Group at EPA where we developed a matching algorithm because the way that the pollution prevention law in the US works is that it's a carrot style law. So you get a pat on the back if you do well. You don't get sanctioned really. You kind of get helped if you do bad. Helps like, and so their agenda was, okay, so if you have facilities that do a pollution prevention action, maybe there's another facility out there who could do the exact same pollution prevention action, but they just don't know about like what some other facility in their, sort of peer group did. And so we developed a interactive like tool where facility managers, which is what we hoped would use it, or who we hoped would use it, could put in their facility characteristics like the processes they use, the chemicals they use, the environmental context in which they operate, the sector in which they operate, and then we try and match them with a good actor in the space of pollution production, and then connect those two people via telephone. And that the EPA really loved, but I think that it was a little wonky. We used Shiny to do it, and we were not as expert at Shiny development as we are now. So I think that those types of matching algorithms would really help support like change, because the law is really written to celebrate people who do good things rather than beat down people who do sort of not good things. And on the community composition side, that's a harder case, I think, because you're sort of usually dealing with communities that have legacies of toxics that they're managing, and so the sort of co-creative and support for those places is a really important aspect. And talking to a community that is dealing with cancer is, they don't really care how to the ninth decimal point they're being impacted, right? So usually in those scenarios, like I'm currently working with Environmental Defense Fund in Port Arthur, Texas, there's so much need for like, how do I argue that our cancer footprint is bigger than someone else's cancer, some other community's cancer footprint, and it's because of this proximate facility. So on that side of things, I think there are a lot of like environmental justice projects that are completely stimulating and exciting from the standpoint of the academic side. It's just like the moment you talk to a community that's dealing with these types of things, I am more compelled to like, what can I do to like help your argument than write another paper. But my chair or my dean probably wants another paper too. So yeah.
Can I ask you? Oh, I'm sorry.
Sure. Right. So that's where like having a more formal like regression scenario would be helpful. Like I could tell you more about like, is it because they're living in an area of like lower regulatory surveillance? Is it because they're all in the chemical sector? Is it because they all are, child companies of complex parent organizations? Is it because they're all located in environmental justice communities? Is it because they were grandfathered in the Clean Air Act? Is it because they have, some really critical product that they make that, and so my answer to you is going to be dissatisfying because I don't think we really know all of that. We have a few models that try and operationalize some of those things that are not, quite published yet. But one of the other complexities I can introduce here is that the actors located in the tails of this distribution change year over year. There are facilities that are more consistently in the tail than not, but we're not really talking about, whack that one mole and we're done. We're talking about a, sort of complicated system that generates these outliers, and it's hard to know exactly why. But the direction we're moving is trying to do that in a more formal regression modeling framework that incorporates uncertainty effectively.
The quality science communication is central to a large part of not just what you do, but where your students and other people that you're pushing through your group what they're going to need in their career. So what are you doing to address that specifically for your students?
In terms of science communication.
Science communication.
Yeah.
Straightforward. So
Yeah. So, the students that I've had in the past, a lot of them go to EPA and are, we had for really not as much recently, but in the past, we had a Tuesday enforcement call with EPA every single week. So all the students, would listen in and get to know everybody. And so we go to EPA anytime we're invited. I think that probably could do a better job of like engaging with science communication more effectively. And I think that every time I do a talk, it sparks some interest in that. But I don't think I've fostered a really big science communication role in my students. It's like R coding, and once we get that, it's some parallel computing, and then yeah.
Yeah, because within IACS, we've sort of had various thrusts to make that happen, and there was a national research training grant that Heather and others that you were already involved in. So I'd love to have a broader conversation about that.
That would be great.
Any last questions? Okay. Oh yeah. I'll just ask you.
Whatever.
Yeah, very good. Okay. Let's first thank Mary.
Thank you.